Everything you have ever seen, every star, every galaxy, your own body adds up to about 5% of what the universe is made of. The other 95% is invisible, and it comes in two kinds, one that pulls galaxies together and one that pushes the whole universe apart. We call them dark matter and dark energy, and tonight we are going to ask the simplest possible question about them. Where exactly did they come from? The answer is stranger than the mystery, because it turns out we have been asking one question when we should have been asking two. So get comfortable, turn the lights low, and settle in. The universe is mostly missing, and we are going looking for it. Part 1. 95% of everything is missing. I want to begin tonight with a fact that sounds like a mistake. The kind of sentence you read twice because surely the words got scrambled on their way to the page. Everything you have ever seen, every star in every photograph ever taken, every planet, every cloud of glowing gas strung between the galaxies, the entire shining inventory of the cosmos, and your own body lying there in the dark as you listen to this. All of it together adds up to about 5% of what the universe is actually made of. The other 95% is invisible. And not invisible in one way, but in two completely different ways, as if the universe were keeping two separate secrets and hoping we wouldn't notice that they were secrets at all. The numbers themselves are worth sitting with for a moment, because they are easy to say and almost impossible to feel. Roughly 27% of the universe is something we call dark matter. Roughly 68% is something we call dark energy. And the leftover sliver, the 5%, is ordinary matter, the stuff of atoms, the stuff of chemistry, the stuff that makes stars burn and makes you. To put it in terms you can hold in one hand, imagine the entire contents of the universe as $20 on a table. One single dollar of that is everything you have ever been able to point a telescope at. The rest is two kinds of darkness you can feel only by what they do. What makes this stranger still is how recent all of it is. For most of human history, people assumed that what they could see was more or less what there was. The sky was full of stars, and the stars were the universe, and the dark gaps between them were simply empty. It was only in the last century that the gaps turned out to be the main event. The first hints came in the 1930s, the firm evidence in the 1970s, and the discovery that the largest ingredient of all is some unseen energy pushing space apart did not arrive until 1998, well within a single human lifetime. So when I tell you that 95% of the universe is invisible, I am not describing some ancient settled wisdom. I am describing one of the freshest and most humbling discoveries our species has ever made the realization, arriving only in the last few decades that we had been studying the foam and calling it the sea. So here is the question I want to follow tonight, the one written into the title, and I want you to notice how innocent it sounds. Where, exactly, did these two invisible oceans come from? Where does something that outweighs every star and galaxy combined actually come from? It is the kind of question a child asks, and the kind a physicist spends a lifetime failing to fully answer, and somewhere between those two is where the most interesting things tend to live. But I have to tell you something right away, because it changes how the whole night unfolds. That question contains a trap, and the trap is hidden in the word "and." Dark matter and dark energy are almost always spoken in the same breath, as though they were a matched pair, two halves of one mystery, brother and sister born of the same parents. They are not. They are almost certainly not the same kind of thing at all, and they almost certainly do not share an origin. They were married to each other by a single word, dark, and that word means nothing more profound than we cannot see it. We gave two strangers the same surname and then spent decades assuming they were family. Look at what each one actually does, and the difference is immediate. One of them clumps. It gathers, it pulls things toward itself. It builds invisible scaffolding around galaxies and holds them together. It behaves in every way that matters, like matter, like stuff, like a substance, like a noun. The other one does the opposite. It does not clump or gather anywhere. It pushes. It stretches space apart, gently and relentlessly, everywhere at once, like a pressure built into the emptiness itself. One pulls inward and one pushes outward. One looks like a leftover, the other looks like a property of space. And that single contrast is the spine of everything I am going to tell you tonight. So let me say plainly where we are heading without giving away the ending. Dark matter has something like a birth certificate, and we can almost read it. We know roughly when it formed, not the year, obviously, but the era, a specific sliver of the first second after the universe began. What we do not know is what it is. We have its date of birth and a blank space where the name should be. Dark energy is stranger. Dark energy may have no birth certificate at all, because dark energy may never have been born. It may simply be a feature that empty space has always carried, present from the very first instant, only becoming noticeable much, much later. And asking where something like that came from may turn out to be a little like asking what color the number 7 is. I will be honest with you about the shape of tonight, because I think honesty is more comfortable than false suspense. This is not a video that ends by handing you a tidy solved answer with a bow on it. Nobody has that answer. This is a video about learning to ask the question more honestly than the title asks it. It is about the slow, strange pleasure of discovering that what you thought was one mystery is actually two, and that the two pull in opposite directions, and that getting comfortable with two open questions is somehow more satisfying than pretending you have closed one. Let me ask you something before we go further, something I genuinely want you to try. When you say the word nothing or the word came from, you are quietly assuming that there was a time when the thing wasn't there, and then a moment when it was. That is what an origin is, a before and an after. But what if one of these two oceans was always there? What if the question, where did it come from, simply does not apply to it? The way, what is north of the North Pole, does not apply to a direction. Hold that thought loosely. We will need it later, and it will not feel as abstract by the time we arrive. So here is how the journey will go, and you do not need to memorize any of it. You only need to settle in. First, we have to make sure these two things are even real, because it is a fair and serious question to ask how anyone could possibly be certain about something they have never seen. Then we will take dark matter by the hand and walk it backward, all the way back toward its beginning, and we will find a factory that ran for a fraction of a second and then shut its doors forever. Then we will take dark energy and walk it backward too, and we will find that the path does not lead to a factory at all. It leads somewhere far more disorienting. And the fact that these two walks end in two such different places is, I think, the most beautiful and underappreciated fact in all of cosmology. This is going to be a long, slow walk, the kind best taken lying down with the lights off. So get yourself comfortable, pull the blanket up. There is no hurry at all tonight. We are going to travel back to the first second of time itself, and we have all the time in the world to get there. Because before we can ask where these things came from, we have to answer a harder and more immediate question, one that any reasonable person would demand an answer to first. How do you find something you cannot see? How can anyone stand here, in a universe where 95% of everything is invisible, and claim with a straight face to know it is there at all? The answer to that turns out to be one of the great detective stories in the history of science, and, like all good detective stories, the way the culprit was caught tells you almost everything about who the culprit is. Is less than break time equals 1s, is greater than number, part 2, the detectives who caught the invisible. Every origin story has to begin with a detection, and I want you to keep one idea in your mind as we go through this part, because it is the quiet key to the whole night. The way each of these invisible things was caught is itself the first clue to where it came from. How you find something tells you what kind of thing it is. So as we meet the detectives, listen for what each piece of evidence is secretly whispering about birth. The first detective did not even know he was opening a case. His name was Fritz Zwicky, a brilliant, abrasive, famously difficult Swiss astronomer working in California, and in 1933 he was studying a great swarm of galaxies called the Coma Cluster. He measured how fast those galaxies were moving around inside the swarm, and he found something that should have been impossible. They were moving far too fast. They were racing around so quickly that the gravity of all the visible matter, all the stars, all the glowing gas, was nowhere near enough to hold the cluster together. By every calculation he could make, that cluster should have flung itself apart long ago, its galaxies scattering off into the darkness like sparks from a fire. And yet there it was, intact, held together by something. Zwicky proposed that there must be a great deal of unseen mass, providing the missing gravity, and he gave it a name in his native German, Dunkel Materie, dark matter. And then, because science does not always reward the people who are right too early, he was largely ignored for the better part of 40 years. The case went cold until a second detective reopened it, and this time the evidence was impossible to wave away. Her name was Vera Rubin, and in the 1970s, working with her colleague Kent Ford, she did something almost stubbornly simple. She measured how far stars orbit within individual spiral galaxies. Now, here is what everyone expected her to find, and it is the same thing you would expect if you thought about our own solar system. Out near the edge, far from the center, the stars should move slowly, because most of the galaxy's mass, all those crowded inner stars, is behind them, pulling from the middle, and the farther out you go, the weaker that pull should get. The planets near the sun move fast, the distant ones crawl. That is how gravity is supposed to work when the mass is concentrated in the center. That is not what she found. Vera Rubin found that the stars at the very edges of spiral galaxies were orbiting just as fast as the stars much closer in. The speed did not drop off. It stayed stubbornly, flatly high, all the way out, and then kept going, out past the visible edge of the galaxy entirely. There was only one way to make sense of it. Each galaxy had to be embedded inside an enormous, invisible halo of mass, a sphere of unseen material reaching far beyond the glowing disk, its gravity gripping those outer stars and whipping them around at high speed. The visible galaxy, the beautiful pinwheel of light, was just the bright center of something far larger and completely dark. Those measurements, the rotation curves, are still today the bedrock evidence that dark matter is real. Vera Rubin did not get the Nobel Prize she deserved before she died, which is one of the quiet injustices of modern science, but she changed our picture of the universe permanently. Then the evidence began to arrive from every direction at once. There is a phenomenon called gravitational lensing, and it comes straight out of Einstein. Mass bends space, and light follows the bends, so a heavy enough object acts like a lens, distorting and magnifying the light of whatever lies behind it. When astronomers look at clusters of galaxies, they see the light of far more distant galaxies smeared into arcs and rings, bent by gravity. And when they measure how much bending is happening, they can weigh the cluster, they can map exactly how much mass is there and where it sits. Again and again, the answer comes back the same. There is far more mass than there is visible matter, and the invisible mass is mapped out in great unseen halos and rivers, sketched for us by the bent light of the galaxies behind them. But the single most persuasive piece of evidence, the one that I think would convince almost anyone, came from a cosmic collision. Out in the distance, there is an object called the Bullet Cluster, And it is not one cluster, but two, caught in the act of having smashed straight through each other. When you watch a collision like that, the ordinary matter, the hot gas that makes up most of the normal mass, behaves the way you would expect. It crashes. The two clouds of gas slam together, they drag on each other, they slow down, they pile up in the middle, and they glow furiously in X-rays from the violence of it. But when astronomers used gravitational lensing to map where the actual mass of the two clusters was, they found something astonishing. The mass had not piled up in the middle. The mass had sailed straight through, untouched, and was sitting far out ahead on either side, exactly where the galaxies were, having passed through the collision as if it weren't even there. I want you to feel why that matters so much, because it is one of the cleanest results in all of physics. In the bullet cluster, the location of the mass and the location of the atoms physically separated, they came apart in space. You could point at one spot and say, there is where almost all the matter is, and point at a completely different spot and say, there is where almost all the ordinary stuff, all the gas and atoms ended up. The only way that happens is if most of the mass is made of something that does not crash, does not drag, does not interact the way normal matter does something that simply glides through a collision like a ghost through a wall. That is not a mistake in our equations of gravity. That is stuff, invisible, ghostly, but real stuff, with a location of its own. And then there is the grandest accountant of all, the cosmic microwave background, the faint afterglow of the hot young universe, light that has been travelling for more than 13 billion years. Encoded in the precise pattern of its slightly warmer and slightly cooler patches is a complete inventory of what the early universe was made of, because the way that primordial light rippled depends on exactly how much of each ingredient was present. When cosmologists read that pattern, it tells them, with remarkable precision, that there had to be about 5 times as much dark matter as ordinary matter, gravitating, shaping those ripples, when the universe was only a few 100,000 years old. That is where the famous budget comes from. That is how we know the split is 5%, 27%, 68%. Now, here is the clue I asked you to listen for, and it is everything. Look at how dark matter announced itself in every single one of these cases. It held a cluster together by gravity. It built halos around galaxies by gravity. It bent light by gravity. It passed through a collision while still gravitating. It shaped the ripples of the early universe by gravity, and crucially, by clumping, by gathering into the dense regions that would become galaxies. Every fingerprint dark matter left behind is the fingerprint of something that pulls inward and gathers, exactly the way ordinary matter does, exactly the way a leftover substance would. The detective work itself is already whispering the answer to our question. It is whispering, this is stuff, and it was here early, gathering, building. And now contrast that, just briefly, with how the other ocean was caught, because the difference is the entire reason these are 2 stories and not one. Dark energy was never found by watching things clump together. It was found, as we will see, by watching the whole universe come apart faster and faster, not by a pull, but by a push. And that single difference, pull versus push, gather versus scatter, is the first hard evidence that the title hides 2 completely separate births. We now have 2 confirmed oceans, detected by 2 opposite signatures. One pulls and clumps like a thing that was made. One pushes and smooths like a property that simply is. So let us follow the first one home. Let us take dark matter and walk it backward, into the fire of the first second, and find out what kind of factory could possibly have made a substance that outweighs all the stars 5 times over and never once gave off a single particle of light. Is less than break time equals 1s is greater than number part 3. A fossil from the first second. There is a word physicists use for dark matter that I find quietly beautiful, and the word is relic. A relic is something left over, something manufactured at one time and then carried, unchanged, into a much later age. The helium floating in the universe is a relic. Most of it was cooked in the first few minutes after the beginning and has been drifting around ever since. And dark matter, whatever it turns out to be, behaves exactly like a relic. It looks like something the early universe made in a hurry, in enormous quantity, and then left behind for everything that came afterward to grow on top of. So our question, where did dark matter come from, is really the question, what kind of furnace produces a relic like this, and when did it stop burning? The remarkable thing is that we can date the relic without knowing what it is made of, and the way we do that is by working backward from a simple, undeniable fact. Galaxies exist. Clusters of galaxies exist. The great cosmic web of matter, strung out across hundreds of millions of light years, exists. And none of it could have formed in the time available unless dark matter was already there first, already gathering, already building the invisible scaffolding onto which ordinary matter could later fall. Ordinary matter, in the early universe, was too tightly coupled to light to clump on its own. It was being jostled and blown around like dust in a gale of radiation. Dark matter felt none of that. It ignored the light entirely and began quietly pooling into dense regions long before ordinary matter could, and those dense regions became the gravitational wells that everything else eventually drained into. Without dark matter laying the foundations early, the universe would simply not have had enough time to build a single galaxy. So we can run the clock backward with confidence. We know from the cosmic microwave background that dark matter was already clumping and shaping the ripples of the universe when it was only a few 100,000 years old. But if it was already doing that job so early, it must have been manufactured even earlier, still long before the first atom formed, back when the universe was a fraction of a second old. That is the era we are looking for. Not millions of years, not thousands, not even one full second. The factory we are hunting ran in the opening sliver of time, when the universe was younger than a single heartbeat by an almost unimaginable margin. I want to reframe our question precisely, because precision here is what makes the rest of the night click into place. For dark matter, where did it come from, really means this. By what process did the unbelievably hot, dense, early universe manufacture a substance that is stable enough to still be here today, invisible enough never to have emitted light, slow-moving enough to clump under gravity, and abundant enough to outweigh everything else 5-1, and then, crucially, stop making it at exactly the right moment to leave behind the amount we actually measure? That is the puzzle. Not just how to make the stuff, but how to make precisely that much of it and then quit. This idea of a fixed leftover amount has a name, the relic abundance, and it is worth understanding why it is such a strong constraint. Imagine a factory that runs for a moment and then shuts down forever. Whatever it produced in that moment is all there will ever be. From then on, the product just gets spread thinner and thinner as the universe expands, like a fixed number of raisins in an ever-rising loaf of bread. The total number of raisins never changes after baking begins. So when we measure how much dark matter there is today and account for how much the universe has expanded since the first second, we are effectively reading the factory's final output number, the quantity stamped on the last item before the lights went out. And any theory of dark matter's origin has to reproduce that number exactly. It is a wonderfully demanding test. Let me give you a sense of the timescales, because they are almost comically extreme. When we talk about the moment dark matter was likely produced, we are talking, in the leading scenarios, about somewhere between a trillionth of a second and a trillionth of a second after the beginning. The dark matter sitting in the halo around our galaxy right now, the stuff your planet is ploughing through as it orbits, is older than the first atom by hundreds of thousands of years. It is older than the oldest light in existence. It predates anything a telescope can ever, even in principle, photograph. When you look up at the night sky, every point of light you see formed billions of years after the dark matter that cradles it had already been made and set aside. There is another way we know dark matter is genuinely a different substance, and not just ordinary matter we failed to spot, and it comes from the recipe of the first few minutes. In those opening minutes, the universe was hot enough to act as a nuclear furnace, fusing the lightest elements, hydrogen, helium, a trace of lithium in proportions that depend very precisely on how much ordinary matter was present. We can measure those proportions today, and they tell us, independently, exactly how much ordinary matter the universe contains, and that amount is far too small to be the dark matter. The books simply do not balance with atoms alone. Whatever holds the galaxies together is not faint stars, not cold gas, not ordinary matter hiding in the dark. The early universe's own fusion recipe forbids it. The missing mass has to be something that does not participate in that nuclear chemistry at all, something outside the ordinary roster of particles entirely. So we are not merely failing to see enough stars, we are detecting a substance that the first minutes of the universe insist is not made of the same ingredients as everything else. There is one more property the origin story has to explain, and it is hiding in a single word that cosmologists attach to dark matter: cold. When they say dark matter is cold, they mean it moves slowly compared to the speed of light, and that matters enormously because only slow-moving matter can clump. If dark matter was zipping around at nearly light speed hot in the jargon, it would have streamed straight out of every dense region as fast as gravity tried to gather it, smearing structure out instead of building it, and the universe would look nothing like it does. The fact that we have galaxies at all tells us the dark matter was born cold, or cooled down very quickly. So any factory we propose has to produce not just the right amount, but the right temperament, a substance content to drift slowly and pool, rather than race around and scatter. Keep that requirement in your pocket. It quietly rules some recipes in and others out. And here is where the story opens up, because it turns out there is more than one way the early universe could have cooked this up. Physicists have written down several different recipes, several different factories, and the strange thing is that they disagree with each other in a fundamental way. Some of them say dark matter was once right in the thick of things, jostling shoulder to shoulder with ordinary matter in the fire, part of the crowd, until the universe grew too big and cold, and it got left behind. Others say dark matter was always a stranger, always standing apart, never really mixing with ordinary matter at all, produced in some quieter and lonelier way. One family of recipes makes dark matter a former insider. The other makes it a perpetual outsider. And we genuinely do not yet know which kind of origin story is true, because we have never caught the substance itself. So that is the shape of dark matter's mystery, and notice how different it already feels from anything we will say about dark energy. Dark matter's problem is not that we have no origin story. Dark matter's problem is that we have too many, all of them plausible, all of them placing the birth in that same razor-thin window of the first second, all of them producing a cold, invisible relic, and no way yet to read which recipe the universe actually used. We have a crowded room of suspects, and a date of birth, but no name. The oldest and most elegant suspect, the one that dominated this field for decades and very nearly convinced everyone, says dark matter was once just another particle in the fire until the universe itself grew too large for the particles to keep finding one another. It is a story about a party that ends not because the guests leave, but because the room keeps growing until no one can reach anyone else. It is, in a sense, a cosmic game of musical chairs, and it begins in a furnace. Is less than break time equals 1s is greater than number. Part 4. Freeze Out, a cosmic game of musical chairs. To understand the first and most famous recipe for dark matter, you have to picture the universe in its opening instant, and you have to throw away every image you have of the calm, cold, mostly empty space we live in now. In the first fraction of a second, the universe was a furnace, denser and hotter than the center of any star that would ever form, a seething soup of energy and particles packed so tightly and moving so violently that matter and radiation were constantly transforming into each other. Energy was congealing into particles, and particles were colliding and dissolving back into energy, billions upon billions of times over, in a roiling equilibrium. There was no empty space to speak of. There was only the fire. In that fire, according to this recipe, dark matter particles were just another ingredient in the soup, and they were behaving exactly like everyone else. Pairs of dark matter particles were constantly being created out of the available energy, and pairs of them were constantly colliding and annihilating back into energy, born and destroyed, in perfect balance. As long as the universe stayed hot and dense enough, the population held steady, a fixed crowd, with members constantly leaving through annihilation and constantly being replaced through creation, like a city whose population stays the same even though people are always being born and always dying. The technical name for this balance is thermal equilibrium, and it is the starting condition for the whole scenario. Dark matter, in this picture, was an insider. It was in the crowd. It was part of the fire. But the universe does not stay hot, and that is where the story turns. Space was expanding, and as it expanded, it cooled, and as it cooled, two things began to happen at the same time, both of them working in the same direction. First, the temperature dropped below the point where there was enough energy in an ordinary collision to create a fresh pair of heavy dark matter particles. The creation side of the balance began to shut down. The universe could no longer afford to make new ones. And second, at the very same time, the expansion was thinning everything out, spreading the particles farther and farther apart, so that the existing dark matter particles found it harder and harder to locate a partner to annihilate with. Both halves of the balance were failing together. Creation was being switched off by the cooling, and annihilation was being strangled by the thinning. This is the moment I love, and it deserves a metaphor. So picture a game of musical chairs, but a strange one played in a room that is silently growing larger and larger. While the music plays, while the universe is hot, the players are packed together, constantly pairing off and leaving the floor, constantly being replaced. But the room is expanding. The players are getting farther apart. And then the music stops, the heat fades, and the players can no longer find each other to pair off and exit. Whoever is left standing on the floor at that moment simply stays standing because there is no longer any way for them to leave. Their number is frozen. It does not matter that the room keeps growing for billions of years afterward. The count of players is locked in at the instant they could no longer reach one another. Physicists call this moment freeze out, and it is, in this recipe, the exact moment dark matter's relic abundance was set. The leftover amount we measure today is simply the number of players who were too far apart to pair off when the music stopped. For decades, the leading candidate to be those players had a name, the WIMP, which stands for Weakly Interacting Massive Particle. The idea was that dark matter was made of heavy particles that felt gravity, of course, but otherwise interacted with ordinary matter only through something like the weak nuclear force, one of the faintest forces in nature, the same force responsible for certain kinds of radioactive decay. Such a particle would be almost completely antisocial. It would ignore light entirely, which is why it would be dark. It would pass through ordinary matter and through you and through the entire Earth, almost without ever touching anything. And it would have been a perfectly natural member of that early fire, freezing out at just the right time. Now, I have to tell you about the single fact that made the WIMP idea so seductive that it dominated this field for a generation, because it is genuinely one of the strangest coincidences in science, and it has a name that physicists say with a slightly nervous smile: the WIMP miracle. Here is the miracle. If you take a particle whose mass and interaction strength are set by the scale of the weak nuclear force not chosen to fit dark matter, just the natural scale that shows up independently in particle physics for completely unrelated reasons, and you run the freeze-out calculation, asking how many would be left standing when the music stopped, the math hands you almost exactly the amount of dark matter we actually measure in the universe today. The two numbers, coming from two utterly different directions, one from the physics of the very small and one from the inventory of the entire cosmos, line up. It is as if the recipe for dark matter and the recipe for the building blocks of matter were written in the same handwriting. Nobody knows whether that coincidence is a profound clue or a cruel accident, but it is why so many brilliant people spent so many years certain that the WIMP was the answer. There is a detail in the freeze-out story that I find genuinely beautiful, and it concerns timing, because the moment the music stops is not arbitrary. It is set by a delicate race between two clocks. One clock is how fast the particles can find each other and annihilate, which depends on how dense and hot the universe is. The other clock is how fast the universe is expanding, thinning everything out. As long as the annihilation clock runs faster than the expansion clock, the particles stay in balance, in the crowd, in equilibrium. But the expansion clock is relentless, and the annihilation clock slows as the universe cools, and at the instant the expansion clock finally wins the race, the particles are stranded. So the relic abundance is, in a real sense, a frozen photograph of the exact moment the universe expanded faster than its own ingredients could keep up. Change the strength of the interaction even a little, and you change which clock wins when, and you change how much dark matter survives. That sensitivity is precisely why the WIMP miracle felt so meaningful. The race came out so close to the answer we measure. Notice how perfectly this recipe fits the relic theme we built in the last part. In the freeze-out story, dark matter is the ultimate leftover. It was not made off in some lonely corner. It was right there in the thick of the fire, in equilibrium with everything else, an insider, a full participant, until the expansion of space itself ended the party and stranded a fixed number of survivors. The amount of dark matter in the universe, in this picture, is a fossil record of the exact moment the universe grew too large for its own hottest ingredients to keep interacting. That is a strangely moving thought. The darkness that holds the galaxies together is a monument to the instant the universe became too big for its particles to find each other. And so for decades the hunt was on, and it was a hunt built on confidence. If dark matter is a WIMP, then even though it almost never interacts, almost never is not never. Once in a great while, one of those particles, streaming through the Earth, should bump into the nucleus of an ordinary atom and give it a tiny, detectable kick. So physicists built extraordinary machines to catch that kick. They buried tanks of liquid xenon far underground, beneath mountains and in old mines, shielded from every other source of interference, instruments so sensitive they can register the recoil of a single atomic nucleus. Detectors with names like LUX, Zeppelin, and Xenon have been sitting in the dark for years, holding their breath, waiting for one unmistakable thump from a passing piece of dark matter. And here is the part of the story that has quietly reshaped all of modern physics. They have found nothing. Year after year, the detectors have grown more and more sensitive, now probing for interactions so faint they correspond to fewer than one expected event per ton of detector material per year, reaching into regions of possibility where the WIMP was supposed to be hiding and the tanks have stayed silent, not a confirmed whisper. I want to be careful and fair here, because silence is not the same as disproof. The empty-handed searches have not killed the WIMP idea outright. They have squeezed it, cornered it, shrunk the space where it could possibly be hiding down to a sliver of what it once was. But that long, patient, expensive silence has done something important to the field. It has loosened the WIMP's grip on the imagination of physicists, and it has sent many of them back to the drawing board, taking far more seriously a set of rival recipes they had once treated as long shots. Because what if dark matter was never an insider at all? What if it was never in the party, never in the fire, never one of the crowd? What if it was a stranger from the very beginning, made in some quieter, lonelier way that would leave the underground detectors silent forever, exactly as we find them? Is less than break time equals 1s is greater than number, part 5, other recipes for the same ghost. If freeze out is the story of dark matter starting on the inside and being left behind, then the rival recipes all begin from the opposite premise. And that premise is worth stating clearly because it reframes everything. These recipes assume dark matter was always an outsider. It was never in equilibrium with ordinary matter, never part of the fire, never trading places in the great soup of creation and annihilation. It was a stranger to our kind of matter from the first instant, and it was made in ways that would never leave a fingerprint in an underground tank. And the unsettling thing is that these recipes fit the silence of the detectors perfectly. If dark matter is this shy, then we were never going to hear it thump. The first of these is almost a mirror image of freeze out, and physicists, who enjoy a tidy bit of wordplay, call it freeze in. The particles in this story are sometimes called FIMPs, feebly interacting massive particles, and the key word is feebly. They are coupled to ordinary matter so weakly that they never manage to reach equilibrium at all. Instead of starting with a full population and being left behind, they started with almost none and were slowly dripped into existence, one rare interaction at a time. As ordinary particles in the hot bath occasionally, by chance, produced one. Picture a sealed room and a ceiling that leaks a single drop of water every few minutes. The puddle on the floor builds up gradually, drop by drop, until the room cools to the point where even those rare drops stop forming and the puddle is fixed. Freeze out leaves a crowd behind as the room empties. Freeze in builds a puddle up from nothing as the room slowly seals. Opposite processes, same result. A fixed relic abundance frozen into the universe in the first fraction of a second. The second recipe is stranger and, to my mind, more wonderful because it requires no collisions at all. It is called gravitational production, and the idea is that dark matter may have been created directly by the violent stretching of space itself. At the very end of cosmic inflation, that brief, ferocious episode in the first sliver of a second, when the universe expanded by an enormous factor, in almost no time, the gravitational field of the universe was changing with staggering speed. And here, quantum physics does something deeply counterintuitive. A rapidly changing gravitational field can pull particles straight out of the vacuum, conjuring real, lasting matter from the energy of empty space being violently shaken. No fire required, no soup, no collisions, just space-time itself, expanding so abruptly that it rang like a struck bell, and the ringing left behind a residue of dark matter particles. In this story, dark matter is not a leftover from the fire. It is something space coughed up as it tore itself open. This is where our origin story brushes right up against the cutting edge of current research, and I want to flag clearly that what I'm about to describe is frontier work, exciting and unconfirmed rather than settled. In the last couple of years, physicists have realized that some of these early production processes, the gravitational ones, and a related class involving violent transitions in the early universe would not have happened quietly. They would have rung that bell hard enough to send out ripples in space-time, gravitational waves, that should still be washing through the universe today as a faint background hum. In other words, dark matter's very birth may have left a sound, an extremely subtle thrum woven into the fabric of space, a kind of birth cry. And future gravitational wave observatories, instruments being designed right now to listen far more sensitively than anything we have today, might one day be able to hear it. Think about what that would mean. We have never seen a dark matter particle, but we might, someday, hear the faint ringing of the moment it was made, not detect the thing itself, but detect the sound of its creation, still trembling through space 13 billion years later. As of now, this is a hope, a theoretical prediction waiting on instruments that do not yet exist. But it is a real one. There are other recipes still, and they are worth knowing because each has its own devoted following. There is the axion, an absurdly lightweight particle that was not invented to explain dark matter at all. It was proposed to fix an unrelated and embarrassing little problem in the theory of the strong nuclear force, a question of why a certain symmetry seems so perfectly obeyed when it didn't have to be. The axion solved that problem elegantly, and then physicists realized that, almost as a bonus, it would also have been produced in the early universe in just the right way to be dark matter. It was made not in a hot collision, but through what is called the misalignment mechanism, in which a cosmic field, initially sitting in the wrong spot, slowly rolled into place like a ball settling into the bottom of a bowl, and the energy of that settling became a sea of ultralight particles. As the WIMP has faltered in the silent detectors, the axion has risen fast, and there are now experiments built specifically to coax these feather-light ghosts into revealing themselves. And there are sterile neutrinos, a heavier and even more antisocial cousin of the ordinary neutrinos that already stream through you by the trillions every second. Ordinary neutrinos barely interact with anything. Sterile neutrinos would interact even less, hence the name. And they would have been produced through subtle quantum oscillations in the infant universe, ordinary neutrinos occasionally morphing into their reclusive relatives. They are another candidate relic, another possible answer, another suspect in an increasingly crowded room. Now step back with me and look at all of these recipes laid out together, because there is a pattern here that is the entire point, and it is easy to miss in the parade of names. Freeze out, freeze in, gravitational production, axions, sterile neutrinos, these mechanisms could hardly be more different from one another in their details. One is an insider left behind, one is an outsider dripped in, one is conjured by expanding space, one is a field rolling into place, one is neutrinos morphing in the dark. And yet every single one of them places dark matter's manufacture in the same impossibly narrow window, the first second, often the first tiny fraction of the first second. Every one of them produces a cold, stable, invisible relic. Every one of them stops producing at the right moment to leave the abundance we measure. We are not short on origin stories for dark matter. We are drowning in them, and we cannot yet read which one the universe actually used. I want to be honest about exactly where that leaves us, because the honesty is more interesting than false certainty. These are competing hypotheses, each motivated by a different idea in particle physics, each mathematically respectable, and the data we currently have, how much dark matter there is, and how it is spread across the sky, constrains the how much and the how clumpy, but it does not yet tell us which factory was running. We are in the position of an archaeologist who has found an enormous, beautifully preserved artifact, can date the layer of rock it came from, to within a hair, can describe its weight and shape and behavior in exquisite detail, and still has absolutely no idea what it was made of or who made it. The date is certain, the substance is a blank. But here is what I most want you to carry forward into the second half of the night, because it is the hinge on which the whole title turns. Look closely at what every one of these dark matter recipes has in common, underneath all their differences, they are all stories about making a thing. Freezing it out, dripping it in, conjuring it from space, rolling it into a field, these are all manufacturing processes. They all assume there was a moment when the dark matter was not there, and then a process, and then a moment when it was. They all have a before and an after. Dark matter's question, in every version, is fundamentally a manufacturing question, and that is why it has a date of birth at all. Hold on to that thought. Hold it tight, because when we turn to dark energy in a few minutes, the most disorienting thing we will discover is that its question may not be about manufacturing anything at all, that it may have no before, no after, no moment of making. But before we cross over to that far stranger ocean, there is one last dark matter candidate to meet, and it is the one that needs no new particle whatsoever, the one that says the answer might be made of something we already know exists, just from an impossibly early time. Is less than break time equals 1s, is greater than number, part 6, black holes older than stars. There is a candidate for dark matter that I find quietly thrilling, precisely because it requires us to invent nothing new at all. And the idea is this: maybe dark matter is not an undiscovered particle hiding from our detectors. Maybe it is black holes. Not the black holes you are picturing, the ones formed when a giant star runs out of fuel and collapses at the end of its life, but a far older and stranger kind called primordial black holes, formed not from dying stars, but directly from the chaos of the infant universe itself. The picture goes like this. In the first instance, after the beginning, the universe was not perfectly smooth. It had ripples, regions slightly denser than their surroundings. Most of those ripples were gentle, and they would eventually grow into galaxies and clusters over billions of years. But if some patches were dense enough, extreme enough, they would not have waited billions of years to collapse. They would have collapsed immediately, under their own gravity, in the first fraction of a second, folding up into black holes long before the first star, long before the first atom, long before there was any light in the universe at all. Black holes older than starlight. That is what a primordial black hole is. The appeal of this idea is its sheer economy, and economy is a thing physicists love. It asks us to add no new particle to the universe, no axion, no WIMP, no sterile neutrino, nothing that has stubbornly refused to appear in any detector. It asks only for gravity, doing exactly what we already know. Gravity does pulling dense regions together until they collapse, operating extremely early and extremely violently. The dark matter, in this story, would be a swarm of these ancient black holes, scattered through every galaxy's halo, dark by definition because nothing escapes them, gravitating away exactly as dark matter must. For a while, this idea seemed to have been ruled out for the smallest black holes, and the reason was Stephen Hawking's famous discovery that black holes are not entirely black, that they slowly evaporate, leaking energy and shrinking over time, with the smallest ones evaporating fastest. By that logic, any primordial black hole small enough to be an interesting dark matter candidate should have evaporated away to nothing long ago. But here is a genuinely recent twist, work from just the last couple of years that has reopened the case. A new idea, sometimes called the memory burden effect, suggests that once a black hole carries enough information about everything that fell into it, that very information load may stabilize it, dramatically slowing its evaporation, meaning small primordial black holes might not have vanished after all. They might still be out there, drifting, intact, far more long-lived than Hawking's original calculation implied, which quietly resurrects them as a viable piece of the dark matter. I should be straightforward that this remains a constrained and partial idea rather than a complete answer. We have searched for primordial black holes in clever ways. They would occasionally bend the light of background stars as they passed in front, a tiny brightening called microlensing and they would have left fingerprints in the cosmic microwave background, and those searches limit how many there can be in most mass ranges. The current consensus is that primordial black holes probably cannot account for all of the dark matter across every possible size, though they may well make up some of it. They remain a live, motivated, partial candidate, and another reminder of how open this question still is. But notice, even here, even with this most exotic of options, where the story lands, because it is the same place every dark matter story lands. Whether dark matter is a particle frozen out of the fire, or a particle dripped in, or a particle conjured by expanding space, or a swarm of black holes collapsed in the first instant, every single version is a story about something the early universe made and then left behind. A relic. A fossil from the first second, manufactured and abandoned, carried forward unchanged into our age. That is the one thing all of dark matter's wildly different origin stories agree on, and it is exactly the kind of origin that the other great darkness, the one that pushes instead of pulls, is about to refuse to have. Because when we turn now to dark energy and ask it the same simple question, where did you come from? It is going to look back at us and, in the most unsettling way imaginable, suggest that it never came from anywhere at all, is less than break time, equals 1s, is greater than number, part 7, the day the universe began falling upward. For almost the entire 20th century, everyone who studied the universe agreed on one thing about its future, and the agreement was so total that the only real debate was about the details. The universe was expanding, that much had been known since the 1920s, and gravity, the great attractor, the force that pulls all matter toward all other matter, must be slowly putting the brakes on that expansion. The only question worth arguing about was how hard the brakes were. Maybe gravity was strong enough to halt the expansion entirely and pull everything back into a final collapse. Maybe it was too weak, and the universe would coast outward forever, slowing but never stopping. Everyone expected to find deceleration. The whole question was just how much. In 1998, two rival teams of astronomers set out to measure that deceleration precisely, and they found something that, by their own accounts, frightened them. They were not slowing down. The expansion of the universe was speeding up. Far from putting on the brakes, the universe had its foot on the accelerator, and the rate at which galaxies are flying apart has been increasing for billions of years. It was one of those rare moments in science when the answer to a careful measurement is not a refinement of what everyone believed, but a flat contradiction of it, and it sent a shock through cosmology that has never fully settled. The way they discovered it is worth understanding, because it is a small marvel of cosmic ingenuity. The teams were measuring a special kind of exploding star called a Type Ia supernova. These explosions are extraordinarily useful because they all detonate at very nearly the same true brightness. They are what astronomers call standard candles. If you know how bright something truly is, then how bright it appears to you tells you exactly how far away it must be, the same way you could judge the distance to a candle of known wattage across a darkened room by how dim it looked. So the teams measured the apparent brightness of supernovae in distant galaxies, calculated their distances, and compared those distances to how fast the galaxies were receding. And the distant supernovae came back fainter than they should have been. They were farther away than a decelerating universe could account for. The only explanation that fit was that the expansion had been accelerating, carrying those explosions to greater distances than steady coasting or slowing ever could. The discovery was so solid and so revolutionary that it won the Nobel Prize in 2011, and it forced cosmology to admit a new and dominant ingredient into the universe, something pushing space apart, something with, in effect, negative pressure. We call it dark energy. To describe this pushing thing, physicists reach back, a little sheepishly, to an idea Einstein had abandoned decades earlier. When Einstein first wrote down his equations of gravity, he believed, like everyone of his era, that the universe was static, neither expanding nor contracting. But his own equations refused to sit still. They insisted the universe must either expand or collapse. So he added an extra term by hand, a kind of constant pressure built into space itself that could balance gravity and hold the universe steady. He called it the cosmological constant, and he gave it the Greek letter lambda. Then, when Hubble showed that the universe was in fact expanding and didn't need to be held still, Einstein threw the term away and reportedly called it the greatest blunder of his life. The supernova discovery of 1998 pulled that discarded blunder back out of the trash, dusted it off, and made it the leading description of dark energy. Einstein's worst mistake turned out to describe 68% of the universe. Now I need to focus your attention on the one property of the cosmological constant that decides everything about its origin, because this is the hinge of the whole second half of the night. The cosmological constant behaves like an intrinsic energy of empty space, an energy that every cubic meter of vacuum simply possesses, just by being space. And crucially, that energy density does not dilute as the universe expands. Think about how strange that is. Ordinary matter thins out as space grows. Spread the same atoms through a bigger volume and the density drops. Even radiation weakens as space stretches. But the energy of empty space, if that is what dark energy is, stays at exactly the same density no matter how much the universe grows, because it belongs to the space itself. Make more space, and you simply make more dark energy at the same strength everywhere. The vacuum does not get diluted, it gets multiplied. I want to slow down on the idea of negative pressure for a moment, because it is the part people find hardest to picture, and it is genuinely counterintuitive. Pressure, in everyday life, pushes outward. The air in a balloon presses against the rubber. So, you might expect that something with pressure would push space outward. But in Einstein's gravity, pressure itself has weight. Pressure gravitates, and positive pressure actually pulls inward, adding to the attraction. To make space accelerate apart, you need the reverse. Negative pressure, a kind of tension, like a stretched rubber sheet that pulls rather than pushes. And dark energy, whatever it is, behaves like a tension woven through every cubic meter of space, so taut and so universal that its gravitational effect flips the usual sign and drives the expansion to speed up. It is not pushing the galaxies apart like an explosion. It is more as if space itself were under a gentle, unrelenting strain that grows simply because there is more and more space to be strained. That single property explains one of the most puzzling features of our universe, the timing. Why did the acceleration only switch on a few billion years ago? Why not at the beginning? The answer falls right out of what we just said. In the early universe, everything was packed close together, and matter was dense, so the inward pull of gravity from all that matter easily overwhelmed the faint, constant push of the vacuum. For billions of years, gravity was winning, and the expansion was actually slowing down, just as everyone had always assumed. But as space kept expanding, matter kept thinning out, its density dropping lower and lower, while the energy of the vacuum stayed exactly as strong as it had always been. And there came a crossover point, around 5 to 6 billion years ago, when the universe was roughly half its current age, when the thinning matter finally lost the tug-of-war and the constant push of the vacuum took over. From that moment on, the universe began to accelerate, and it has been accelerating ever since. Dark energy did not arrive late. It was always there, at the same quiet strength. It simply waited patiently for the universe to empty out enough for its push to be felt. And here we arrive at the disorienting center of dark energy's origin story, the thing that makes it so profoundly different from dark matter. If dark energy is the cosmological constant, if it is simply the intrinsic energy of empty space, then asking where did it come from may be a question with no answer, not because we are ignorant, but because the question may not apply. The cosmological constant is not a substance that was manufactured at some moment in the first second and then left behind. It is not a relic. It has no factory, no freeze-out, no production mechanism, no before and after. It is a property that space simply has, present from the very first instant of the universe, as fundamental to the vacuum as its three dimensions. Asking where it came from might be like asking where the emptiness of empty space came from, or what the volume of a box is made of. It is not a thing in the universe. It may be a feature of the universe. Sit with the contrast for a moment, because it is the whole point of tonight. Dark matter is a noun. It is stuff, manufactured early, a relic the universe made. Dark energy may be an adjective, a quality of space, not a substance within it. We have spent this entire night chasing dark matter's birth certificate and finding too many possible parents. And now we turn to dark energy and find that it may have no birth certificate to chase, because it may never have been born. One of our two great darknesses has a date of birth and no name. The other may have a name, the energy of the vacuum, and no birth at all. But I called this the energy of empty space, as if that settled things, and I have to walk that back, because it does not settle anything. It only relocates the mystery, and it relocates it into one of the deepest pits in all of physics. Because the moment physicists tried to actually calculate that energy to take this idea seriously and compute how much energy empty space should contain, from the principles we already trust, they produced a number. And that number is so catastrophically, so absurdly, so embarrassingly wrong that it has earned a title no theory ever wants. It is often called, without much exaggeration, the single worst prediction in the entire history of science. To understand why dark energy's origin is such a torment, you have to understand exactly how empty space refused to add up. Is less than break time equals 1s is greater than number. Part 8. The worst prediction in the history of physics. To see how badly empty space breaks our equations, you first have to abandon the idea that empty space is empty, because according to our best theory of matter and forces, quantum field theory, the framework underlying nearly all of modern physics, the vacuum is anything but quiet. In quantum field theory, every kind of particle is really a ripple in an underlying field that fills all of space, and these fields can never be perfectly still. Even in their lowest possible energy state, even with every particle removed, the fields retain an irreducible jitter, a residual trembling called zero-point energy. The vacuum seethes with it. Particle-antiparticle pairs are constantly flickering into existence and annihilating again, borrowing energy for the briefest of instants before paying it back. Empty space, looked at closely enough, is a froth of restless quantum activity. This is not speculation. The reality of these vacuum fluctuations has been confirmed in the laboratory through subtle, measurable effects. So here is the beautiful idea, the one that would tie dark energy's origin up in a tidy bow. That seething zero-point energy of the vacuum, that ever-present quantum jitter in every cubic meter of empty space, is itself a form of energy. And energy, according to Einstein, gravitates, and energy built into space that does not dilute is exactly what a cosmological constant is. So perhaps dark energy is nothing more exotic than the quantum vacuum's own restless energy, the unavoidable trembling of the fields gently pushing space apart. If that were true, dark energy would not be a mystery substance at all. It would be the natural, calculable consequence of physics we already know. Its origin would be the quantum vacuum, and the question would be answered. There was only one thing left to do to confirm this lovely story, and that was to calculate the number. Add up the zero-point energy of all the quantum fields in a region of empty space and compare it to the dark energy we actually measure pushing the universe apart. And when physicists did that calculation, the universe handed them a humiliation. The vacuum energy that quantum theory predicts is not a little larger than the observed dark energy. It is not twice as large, or 1,000 times, or 1,000,000 times. It is larger by something like 120 orders of magnitude, a 1 followed by 120 zeros. Depending on exactly how you do the accounting, the figure shifts, but the gap is always somewhere in that monstrous range. I want to try to convey how preposterous 120 orders of magnitude really is, because the words slide right past you otherwise. It is not the kind of error you make by being a bit sloppy. It is not even the kind of error you make by being wildly, comically sloppy. Imagine trying to estimate the number of atoms in the entire observable universe, a number with about 80 zeros after it, and being off by more zeros than that. The mismatch between what our best theory of the vacuum predicts and what we actually measure is the largest gap between theory and observation anywhere in all of science, by an enormous margin. There is nothing else even close. Physicists, who are usually careful and understated people, simply call it the worst theoretical prediction in the history of physics, and they are not really exaggerating. It is worth being fair to the physicists here, because they are not fools, and the size of the error has been argued over carefully. The exact figure depends on assumptions, on where you decide the rules of quantum field theory stop being trustworthy, and on subtleties about how the energy of empty space must look the same to every observer, no matter how fast they move. Take those subtleties properly into account, and some careful treatments shrink the mismatch from 120 orders of magnitude down to something more like 60. But pause on what that supposed improvement actually means. We are congratulating ourselves on being wrong by only 60 orders of magnitude instead of 120 wrong by a mere 1 followed by 60 zeros. That is the state of the art. Even the most generous, most carefully argued version of the calculation leaves a gap so enormous that calling it an open problem feels almost polite. The vacuum energy is either the answer to dark energy and we cannot compute it, or it is not the answer and we do not know what is. This embarrassment has a formal name, the cosmological constant problem, and you can state it as a brutal fork in the road. Either the enormous vacuum energy that quantum theory insists must be there is somehow almost perfectly cancelled out by some unknown mechanism, cancelled not approximately, but to something like 120 decimal places, an act of fine-tuning so precise it beggars belief, leaving behind only the tiny whisper we observe. Or our picture of the vacuum is missing something so fundamental that the entire calculation is meaningless. Either reality is balanced on a knife edge of impossible precision, or we do not understand empty space at all. Neither option is comfortable, and after decades of brilliant effort, no one has resolved it. People have tried, of course, and the attempts are worth knowing because each one is a window into how physicists think when they are cornered. One hope was a beautiful symmetry called supersymmetry, in which every known particle would have a heavier partner, and the contributions of particles and their partners to the vacuum energy would cancel each other out almost exactly, taming the monstrous number down to something gentle. It was elegant, and it was widely believed, and the particles it requires have stubbornly failed to appear in our most powerful colliders. Others have proposed that gravity itself behaves differently than we think on the largest scales, or that the vacuum energy is somehow non-local, smeared across the universe in a way that softens its effect. And then there is the most provocative escape of all, the one that abandons the search for a mechanism entirely and reaches instead for a multiverse. The multiverse idea works like this, and I find it equal parts brilliant and maddening. Suppose our universe is not the only one. Suppose there are countless universes, perhaps an effectively infinite number, each with its own value of the vacuum energy, scattered across every possible amount. In the overwhelming majority of them, the dark energy is the catastrophic, theory-predicted size, and in those universes, space is ripped apart so violently and so fast that no galaxy, no star, no planet, and no living thing could ever form. They are dead before they begin. Only in the vanishingly rare universes where the vacuum energy happens to be tiny and gentle, by sheer accident of the cosmic lottery, can matter clump, stars ignite, planets cool, and observers eventually arise to look around and ask questions. And so, the argument goes, we measure a small, dark energy, not because there is any reason it should be small, but because we could only ever exist in one of the rare universes where it is. Any universe with a large value would have no one in it to do the measuring. The physicist Steven Weinberg used essentially this reasoning to roughly predict the value of dark energy before it was even observed, which is genuinely remarkable. But many physicists find it deeply unsatisfying because it explains the number by appealing to universes we can never see, and it edges out of physics and into philosophy. So look honestly at where dark energy's origin question has led us, and feel how completely different it is from dark matter's. For dark matter, where did it come from? Splintered into a crowd of competing factories, all real, all early, too many to choose between. For dark energy, where did it come from? Splinters into something far stranger. It is the energy of the vacuum, but we cannot compute that energy without being wrong by 120 orders of magnitude. Or it is a property space simply always had, present from the first instant, with no origin at all. Or its value is an accident of which universe we happen to live in, selected by the brute fact of our own existence. Not one of these is a manufacturing story. Not one of them describes a moment of making. Dark matter has too many births, and we cannot pick one. Dark energy may have no birth at all, and we cannot accept it. That, I think, is the truest answer the title can be given as things stand tonight. The two darknesses do not merely have different origins, they have different kinds of origin question. One asks how a thing was made and drowns in possible answers. The other asks how a property came to be and discovers the question may not even be the right shape. And for a long time, this is where the story ended, a relic with too many parents and a property with none. But in just the last 2 years, something has changed. A new machine, staring patiently at millions of galaxies, has begun to whisper a heretical possibility that dark energy might not be a constant after all, that it might be changing even now. And if that whisper turns out to be true, then for the very first time, dark energy would have what dark matter has always had, a history, a before and an after, a beginning. The chance, at last, to actually have come from somewhere is less than break time equals 1s, is greater than number. Part 9. Is dark energy changing its mind? Everything hinges on a single question about dark energy, and now that we have walked through its strange originless origin, you can feel exactly why the question matters so much. Is dark energy truly a constant, fixed and unchanging since the beginning of time, or does it vary? Because if it is a genuine constant, then it has no history, no origin story, nothing to explain except its baffling size. But if it changes over time, if it was a different strength in the past than it is now, then it cannot be a mere property of the vacuum. It would have to be something more like a substance or a field, something with a state that evolves. And anything that evolves has a beginning. The moment dark energy is shown to change, it stops being an adjective and starts being a noun, and suddenly it has a birth story to tell. For most of the time since 1998, all our evidence pointed toward dark energy being a perfect constant, exactly the cosmological constant Einstein had written down. It fit the data beautifully. The standard model of cosmology, the one called lambda CDM, Lambda for the cosmological constant, CDM for cold dark matter, treats dark energy as utterly unchanging. And for a quarter of a century, that simple assumption passed every test we could throw at it. To question it, you would need to measure the expansion history of the universe with extraordinary precision, tracing not just how fast space is expanding now, but how that rate has changed across billions of years. And to do that, you would need a machine of almost absurd ambition. That machine exists, and it is called DESI, the Dark Energy Spectroscopic Instrument. It sits on a telescope in Arizona, and its job is to map the universe in 3 dimensions on a scale never attempted before, measuring the precise distances to millions upon millions of galaxies and quasars, stretching back billions of years. The way it measures those distances is itself a kind of miracle. Frozen into the distribution of galaxies across the sky is a faint, regular pattern, a preferred separation between galaxies, and that pattern is the fossilized imprint of sound waves that rippled through the hot plasma of the infant universe before it cooled. Those primordial sound waves, called baryon acoustic oscillations, left behind a characteristic length, a standard ruler laid down at the beginning of time and stretched ever since by the expansion of space. By measuring how big that ruler appears at different distances at different epochs in cosmic history, DESI can read off how fast the universe was expanding at each stage, and therefore how dark energy has behaved across the ages. In 2024, DESI released its first results, and there was a hint, a faint and tantalizing suggestion, that dark energy might not be perfectly constant. It was not strong enough to make any firm claim, but it was enough to make cosmologists sit up. And then, in March of 2025, DESI released its second major dataset, combining its galaxy maps with measurements of the cosmic microwave background and with supernova surveys. And the hint did not go away, it grew. The combined data pointed, more insistently than before, toward dark energy that is not a constant at all. Dark energy that appears to have been stronger in the distant past and to be gradually weakening now. The push that is driving the universe apart may have been firmer billions of years ago and may be softening as time goes on. If that result holds, and I am going to be very careful about that, if, in a moment, it would be one of the most important discoveries in the history of cosmology, because a true cosmological constant simply cannot do this. A constant is constant, it cannot weaken, but a field can, and this is where an idea called quintessence steps onto the stage. Quintessence treats dark energy not as a fixed property of the vacuum, but as a dynamic field filling all of space, one that can change its strength over cosmic time as it slowly evolves a gentler, slower cousin of the very field that is thought to have driven cosmic inflation in the first instance of the universe. If dark energy is quintessence, then it is something that's switched on, that has a value which rolls and shifts, that had a beginning and will have a future. It would mean dark energy, like dark matter, has an origin we could actually hope to tell. The whole second half of our title's question would, for the first time, have a real answer waiting at the end of it instead of a shrug. The data hold an even stranger wrinkle, and it is worth mentioning because it shows how unsettled this all is. When cosmologists look at the early universe side of the measurements, the numbers flirt with something exotic called phantom dark energy, energy whose density was so extreme in the past that, taken literally and projected into the future, it could point toward dramatic and even violent fates for the cosmos. The late universe data, meanwhile, lean the other way, toward the gentler quintessence picture. The tension between those two regimes is part of why the result is so intriguing and so hard to interpret. Dark energy may be doing something genuinely complicated, something no simple constant could ever capture. We are not relying on DESI alone either. The European Space Agency launched a dedicated spacecraft called Euclid in 2023, and it is a machine built for precisely this purpose, to map the geometry of the dark universe across billions of years of cosmic history, charting how dark matter has clumped and how dark energy has stretched space, with a precision that complements DESI from above the atmosphere. Between the two of them, the ground-based galaxy mapper and the space-based geometer, we are entering the first era in which dark energy's behavior over time can be pinned down rather than merely assumed. After a quarter-century of treating it as a fixed number, we are finally in a position to ask it whether it has been changing all along. There is one more reason this matters, and it reaches beyond dark energy into a crisis that has been quietly troubling cosmology for years. It is called the Hubble tension, and it is this. When we measure how fast the universe is expanding today, using the early universe data, we get one number, around 67, and when we measure it using more direct observations in the nearby, present-day universe, we get a stubbornly different number, around 73. The two measurements should agree, and they refuse to, and no one is sure why. Evolving dark energy is one of the candidate explanations that could potentially reconcile them, which is why DESI's hint reverberates so far. It is not just about one ingredient. It might be a loose thread that, when pulled, unravels and reweaves our whole picture of the cosmos. But I promised you that if, and now I have to honor it, because honesty is the temperament of good science, and I would be doing you a disservice to oversell this, the DESI result is suggestive. It is not settled. It is not a discovery in the way the accelerating universe was a discovery in 1998. The statistical strength of the signal is moderate, the kind of result that has, many times in the history of physics, melted away as more data arrived. Some careful reanalyses published in 2025 have questioned whether the data truly demand evolving dark energy at all, or whether the appearance of evolution is an artifact of how different datasets are stitched together. To turn this whisper into a confirmed fact, we will need more galaxies, more years, more precision, and the verdict is genuinely not yet in. So I want to be clear about what we have. We do not have proof that dark energy has a history. What we have, for the very first time, is a real observational reason to think it might a crack of light under a door that has been sealed since the beginning of time. And that crack is the live frontier of this entire question. If it opens, dark energy will finally have the one thing dark matter has always possessed, a birth. If it closes, we are back to a property with no origin and a number we cannot explain. Is less than break time equals 1s, is greater than number part 10. Could they be the same thing? There is a temptation that I have been holding off this entire night, and I suspect it has been nagging at you too, because it nags at almost everyone who learns about these two darknesses. Wouldn't it be so much tidier if they were the same thing? If dark matter and dark energy were not two separate mysteries, but two faces of a single underlying substance, behaving one way when it gathers and another way when it spreads thin. The human mind craves that kind of unity, and physics has a long, proud record of discovering that things which looked separate, electricity and magnetism, space and time, were secretly one. So it is only natural to ask whether the universe is playing the same trick on us again. People have certainly tried to make it work. There are models of a single dark fluid, one exotic substance that clumps and pulls like matter where it pulls into galaxies, yet pushes like dark energy where it is spread thin across the empty gulfs between them. And there are more modest proposals, including some analyses from the DESI era, exploring whether dark matter and dark energy might at least interact with one another, quietly exchanging energy across cosmic time in a way that would partly braid their two origin stories together. These are real, mathematically serious ideas, and I do not want to dismiss them. But they remain minority positions, because every time someone tries to collapse the two into one, The evidence we walked through earlier tonight pushes back hard. Then there is the boldest move of all, the one that tries to erase both questions at a single stroke, and it deserves a fair hearing. It is called modified gravity, and its most famous version goes by the name MOND. The argument is audacious. What if there is no dark matter and no dark energy at all? What if both are illusions, phantoms we conjured because we are using the wrong law of gravity on the largest scales? Newton's and Einstein's gravity were tested in the solar system, and in the laboratory, the modified gravity advocates point out, and then we simply assumed the same law holds across an entire galaxy and across the whole universe. What if it does not? What if, when you adjust the law of gravity for the faintest accelerations found at the edges of galaxies, the rotation curves that Vera Rubin measured fall out naturally, with no need for any invisible halo? Then dark matter would not need an origin story, because dark matter would not exist. It would be a bookkeeping error in our equations. It is a genuinely clever idea, and it explains some things about individual galaxies more neatly than dark matter does, which is why it has not gone away. But most cosmologists resist it, and they resist it for good reasons that we have already met tonight. Remember the bullet cluster, where the mass and the ordinary matter physically separated in space, where the gravity sat in one place and the atoms sat in another. Modified gravity has a very hard time explaining that, because if gravity simply followed the visible matter under a different law, the pull should stay where the atoms are, and it does not. And remember the cosmic microwave background, whose intricate pattern of ripples is explained with beautiful precision by a universe containing about 5 times as much dark matter as ordinary matter. Modified gravity struggles to reproduce that pattern without quietly reintroducing something that looks an awful lot like dark matter after all. The evidence, again and again, keeps insisting on real, unseen stuff. And at the farthest fringe, I will mention neutrally, there are the truly speculative attempts at unification ideas that our entire universe sits inside a black hole in some parent cosmos, and that relic black holes left over from a great cosmic bounce could be the dark matter, tying the dark sector to the very birth of the universe itself. These are imaginative. They are occasionally dressed up with real equations, and they are nowhere near established. They live in the borderland where physics hands off to speculation, and I flag them as exactly that. But here is the thing I most want you to take from this part. Every single attempt to collapse our two questions into one keeps failing for the same stubborn reason. The evidence simply will not allow it. One darkness clumps and pulls like a relic that was made. The other smooths and pushes like a property that simply is. No matter how badly we want a single elegant answer, the universe keeps handing us two. It is not telling us one birth story with a clever twist. It is telling us two birth stories in two different languages and refusing to let us pretend otherwise. Is less than break time equals 1s is greater than number part 11 two birth stories. We set out tonight to answer what looked like a single, simple question. Where did dark matter and dark energy come from? And somewhere along the way, the question quietly split in two and revealed that it had been two questions all along, two strangers wearing the same word like a borrowed coat. So, let me gather everything we have found and lay the two birth stories side by side, because seen together they are stranger and more beautiful than either is alone. Dark matter's verdict is the verdict of a relic. Almost certainly, it was manufactured in the first second of the universe, in that razor-thin window when everything was fire and density and violence. Perhaps it froze out of the hot soup, like the last players left standing when the music stopped. Perhaps it was dripped in slowly, drop by drop, by a universe too shy to let it ever join the crowd. Perhaps it was conjured straight out of the vacuum by the savage stretching of space at the end of inflation, ringing the bell of space-time so hard that real matter fell out. Perhaps it collapsed into a swarm of black holes older than the first star. We can name the era of its birth with real confidence. We simply cannot yet name the substance. Dark matter's mystery is an embarrassment of riches, too many possible origins, all of them early, all of them plausible, and no way yet to read which recipe the universe actually followed. Dark energy's verdict is the opposite in almost every way. It may not be a thing that came from anywhere at all. It may be the energy of empty space itself, present from the very first instant, the same gentle strength everywhere and always, only becoming visible when the universe had expanded enough for its push to overcome the fading pull of matter. Its mystery is not too many origins but too few, possibly none, paired with a calculation that misses the mark by 120 orders of magnitude, the worst prediction physics has ever made. And yet, in the very last breath of this story, in the data arriving right now from Deci and Euclid, there flickers the possibility that even this is wrong, that dark energy is quietly changing after all, that it has a history we are only beginning to read, that it might, against all our assumptions, turn out to have been born too. We do not know yet. We are standing at the door, and the crack of light beneath it has only just appeared. So here is the honest synthesis, the thing I most want to leave you with as the night winds down. The two largest ingredients of reality were never one mystery. We spent a century calling them by a single name, dark, and that word, meaning only unseen, was the one thing they ever truly shared. One of them is a noun, a substance the early universe manufactured and left behind. The other may be an adjective, a quality that space has always carried with no moment of making at all. They were detected by opposite signs, one by its pull and one by its push, and when we trace them backward, they lead to two completely different kinds of beginning, a factory and a fact, a relic and a property, a thing that was made and a thing that simply is. The deepest discovery hiding inside the title's innocent question is that the question itself was wrong to be a single question. There is a kind of poetry in how perfectly the two stories mirror each other, and it is worth pausing on before we close. Dark matter we caught by its pull and trace back to a moment of making. Dark energy we caught by its push and trace back to no moment at all. One gathers, the other scatters. One built the structures we live among, the other dissolves the distances between them. One is a relic of the universe's hottest, densest, most crowded instant. The other is the quiet property that wins only when the universe grows cold and empty and spread thin. They are not merely two different answers to one question. They are almost opposites in every dimension you can name, in how they behave, in how they were found, in how they began, and in what they are doing to the future. If you wanted to design two ingredients to be as unlike each other as possible, while sharing nothing but invisibility, you could hardly do better than the universe already has. And that, more than any single fact tonight, is why the title's question can never have one answer. You cannot give one birth story to two things that disagree about whether they were ever born. I want to be humble about the limits of all this, because the most interesting chapters are surely still unwritten. It is entirely possible that everything I have told you tonight will look quaint in 50 years. A dark matter particle might finally announce itself in a detector, or in the faint gravitational hum of its own creation, and give the relic its name at last. Dark energy might be confirmed to evolve and gain a real history, or be revealed as a sign that our theory of gravity itself needs rewriting on the largest scales. Some deeper theory might come along in which matter and the energy of space are not the separate things we now believe them to be, and the two birth stories might, after all, turn out to share a single far-off root we cannot yet see. Science is a long conversation, and we have only just learned to ask this part of it properly. But let me end where these questions always, finally, come to rest, which is much closer to home than the first second of the universe. You are built entirely from the bright 5%, the thin film of ordinary atoms that learn to glow and clump into stars and planets, and, eventually, into something that could lie in the dark and wonder about the rest. And you are surrounded, on every side, in every direction, by the two darknesses we have chased tonight. One of them, the relic, is wrapped invisibly around your galaxy this very moment. Its quiet gravity, the only reason the stars did not scatter long ago, the only reason there was ever a stable place for a world like yours to form and cool and grow life. It held the room together so that you could exist. The other, the property of space, is gently and ceaselessly carrying every distant galaxy farther from you with every passing second, stretching the universe toward a future in which the sky will slowly empty and the lights beyond our own neighborhood will, one by one, drift past the edge of what can never be seen again. One darkness built the room, the other will, in the end, quietly clear it. The strangest part of the answer to tonight's question is not that we still do not know where these two oceans came from. The strangest part is that the two things we understand the least are the two things that set the entire stage that gathered the matter, lit the stars, spaced the galaxies, and will one day draw the curtains. We are a brief, bright arrangement of the smallest part of the universe, awake for a little while in a room furnished almost entirely by mysteries, asking, in the dark, where the dark came from. And perhaps that is enough for one night. Perhaps the asking is its own kind of light. Rest now. The two darknesses will keep their secrets a while longer, and they will keep them just as faithfully, whether you are awake to wonder or finally, gently asleep.